Here we go. So we're going to be talking today about non-inertial reference frames. And a non-inertial reference frame is a reference frame that is actually accelerating relative to other inertial reference frames. Now the trick is, notice that this is somewhat of a circular definition, in as much as we're assuming that there's some inertial reference frame out there, and other reference frames are inertial or non-inertial relative to that. But we remember that there's no preferred reference frame, right? So, to an extent, what we're left with is basically saying, well, these reference frames are inertial or mostly inertial. So, for example, the surface of the Earth is a mostly inertial reference frame because it's not accelerating very much. It is accelerating a little bit because we are revolving around our axis, right? So there's going to be some centripetal acceleration going on there. And it's also revolving around the sun. So there's some centripetal acceleration going on there. And the sun is revolving around the center of the Milky Way. So there's acceleration going on there. But those effects are really small. And so unless you're a hurricane, you're not going to notice the acceleration of the Earth. Hurricanes do, by the way. The reason that they spin in, what is it? Counterclockwise? Depends on your hemisphere. And that's because of the rotation of the Earth. So the Earth is a mostly non-inertial, a mostly inertial reference frame. So I want to spin out now two scenarios in which we have some non-inertial reference frames. And this first scenario is an elevator. So here's my elevator. And here am I in the elevator. Okay? When the elevator decides to, let's say, go down, the elevator is going down. Then it has to go from a complete stop to moving with a velocity in this direction to a complete stop down at the bottom. In order to do that, it has to change its motion, and a change in motion means acceleration. That's exactly right. So let's see if we can figure this out. At the very top, when it's just getting into motion, which way is the acceleration going to be pointing? Down, because the elevator has to go from not moving to moving in a downwards direction. Then the elevator gets up to speed. And when it gets up to speed, it moves with a constant velocity, so its acceleration is zero. Exactly so. So in the middle here, the acceleration is zero. And down at the bottom, the elevator has to go from moving down to not moving down, so it experiences an acceleration in which direction? Up. That's exactly right. Now here's the thing. We've all felt this.
The stomach jumping out, and
Yes.
when it stops, you jump.
Yeah, that's exactly right. All of you have been on an elevator, and if the elevator accelerates, it starts to go down, you feel that feeling in the pit of your stomach, like the floor is dropping out from under you, because it is. The elevator is accelerating downwards, and you feel a little bit less heavy as a result. Then, when the elevator gets up to speed, you feel all normal. You tell your friends, you talk to them, and so on and so forth. And then the elevator comes to the bottom, and you feel like you're crunched down into your shoes because you're experiencing an acceleration upwards. So this is an example of a non-inertial reference frame here and here where the acceleration is non-zero. But when the acceleration is zero, then the elevator is an inertial reference frame. Does that distinction make sense to everybody? Okay. Second example. You've got a car. The car is going down the road. We're going to see this from top view. And all of a sudden, the road makes a sharp right turn. Here's my car. And let's say it's going with a constant speed. When the car takes this sharp right turn here, what happens to the passengers in the back seat?
They get flung outward.
They get flung outwards. Which direction? To the left. That's exactly correct. The car at this point right here experiences an acceleration in this direction. How do I know? Because it moved in a circle. And during this portion right here, while the car is moving in a circle, during this portion, the car is a non-inertial or accelerating reference frame. And what I've done is to appeal to your intuitions to say, haven't we all felt that, right? We've all felt that feeling of I'm being flung to the outside. I'm in the elevator, I'm being crunched down into the floor because of the acceleration. So we feel that, we're feeling a force. Okay? Okay. Now, I want to observe something about the force that we feel. And I'm going to observe it like this. Objects in non-inertial or accelerating reference frames experience a fictitious force whose value is equal to negative ma. Now, let me justify that statement in just a moment. But for now, here's what this means. The negative sign here means that the direction of that force is going to be the opposite from the direction of the acceleration. And I want to go back to our examples to see that this is really so. Right here, the car is making a sharp right turn. Which way is it accelerating? It is accelerating towards the center of the circle. Which way do the passengers feel like they're being pulled? Out, away from the center of the circle. You're in the elevator. The elevator drops, so it's accelerating downwards. What do you feel? You feel weightless, like you're being pulled upwards. The elevator comes to a stop at the bottom. It is accelerating upwards. What do you feel? You feel like you're being pushed down into the floor. So you're experiencing this fictitious force that is equal to negative ma. It is the opposite of the direction of the acceleration of the reference frame.
If the acceleration was enough, could you actually get pushed like into the floor?
Sure, that's right. And the easiest way for that to happen would be for the floor to be made out of something like tissue paper or saran wrap, right? And if the elevator now comes to a stop, you tear right through that flimsy floor. Okay? So let me actually prove this statement like this. What we're going to do is we're going to analyze our motion from two different reference frames. We're going to put an object in a reference frame, and the reference frame is going to accelerate in this direction. The reference frame is going to accelerate. Now this is kind of tricky, so I want to imagine the elevator as a prototype for this. So maybe I should have the acceleration downwards, since only Willy Wonka's elevator goes sideways. Okay.
Yeah.
So there's our acceleration right there. Now what we're going to do is we're going to analyze this motion from outside the reference frame first to get our head straight. And then we're going to analyze it inside the reference frame, and we're going to compare notes. If I look at it from outside the reference frame, here's my object right here, then I would say that the sum of forces on the object is equal to mass times acceleration. See? Simple. Okay. So we have sum of forces. Let's call that F net. And there's no problem. Now we're going to come back over, and we're going to reanalyze this from inside the reference frame. Because we are inside that accelerating reference frame, our position is always 0. Our velocity is always 0, and our acceleration is always 0. Right? But now when I do sum of forces, that sum of forces should be equal to 0. But when I add up that sum of forces, I get F net. And F net is not 0. F net is certainly equal to MA over here. What happened? In non-inertial reference frames, Newton's second law breaks. It has to. Because the sum of forces can no longer equal the acceleration inside the reference frame, mass times acceleration inside the reference frame, as well as mass times acceleration outside the reference frame. The sum of forces cannot be two values at once. But there's an easy fix, and that is that we can compensate by adding one more force, the fictitious force, negative MA. And now when I add F net plus negative MA, now that equals 0. Why? Because F net is equal to MA. And this brings Newton's second law back into play here. So mathematically, we can think of the fictitious force as being arbitrarily inserted so as to keep Newton's second law working. So it's not a real force. It's not being caused by anything. It's only being, quote, caused by the acceleration of our reference frame. However, physically, it's real enough so that we feel it. When you drive around that curve, that sharp right curve, everybody in the back seat really does feel like this. But is that what's really going on? It depends on your reference frame. If I examine that car, again, here's the sharp right curve, here's my car, the passengers in the back seat always want to go straight, don't they? And so if they go straight, well, which way is straight? Straight is this way, right? So if they go straight and the car moves out from under them, and look at what happens. The passenger that goes straight here is going to end up further over to the left inside the car. Simply by virtue of going straight, he has ended up to the left of where the car is. The car has turned out from under him. So it's a matter of reference frame. From outside from the inertial reference frame on the outside, we look and we say the passenger just tries to go straight and the car turns. From inside the reference frame, we say the passenger slides to the left inside the car. And you see this with all sorts of nifty things. Anybody ever seen somebody driving down the road with something hanging from their mirror, like the fuzzy dice or something like that?
Yes.
You know what I'm talking about? When you accelerate, what do those fuzzy dice do? And why do they do that? Well, an outside observer would say that the fuzzy dice are standing still and the car is moving around it. But the inside the car, you would say there is some mysterious force that is pushing those fuzzy dice backwards. What is that mysterious force? It is the fictitious force caused by the acceleration of the car. Does that make sense to everybody? Okay. Now, how do we analyze it? Fortunately, the concept is actually harder than the math. The math is really easy. What I want to do is to come back and do a problem using, well, actually, let's do elevator problems first. So we're going to have a 75 kilogram person, who is, of course, a sphere,
Of course.
in an elevator, standing on a scale. Stands on a scale in the elevator. And now the elevator is going to accelerate downwards at, oh, I don't know, how about 1.5 meters per second squared? That's actually a pretty aggressive acceleration for an elevator. And so the question now is, what will the scale read? While the elevator is accelerating.
Like in the middle or at where it starts or it stops?
While the elevator is accelerating, we'll get the same answer. No matter when. As long as the elevator is accelerating.
Wouldn't it be less when it's starting because you feel like you're lighter?
So most elevators accelerate at the very beginning, then they're not accelerating for the vast majority of the trip.
They like accelerate up.
And then they accelerate up at the end.
So when you feel like heavier at the bottom, lighter.
Sure, right. But I'm talking about while the elevator is accelerating downwards at 1.5 meters per second squared, no matter when that happens. Okay. All right. Good. So we can analyze this from one of two ways. If we do the usual inertial reference frame, then we would do sum of forces equals mass times acceleration, free body diagram, and there is a 750 Newton weight pulling down, and there is a normal force pushing up. That normal force is what the scale actually reads. The scale doesn't really read your weight. It really reads the normal force that you're putting on, right? That it's putting on you. And so in the inertial reference frame, we would say that the sum of forces, which is equal to Fn minus 750, spelled with a 7, is equal to mass times acceleration, or 75 kilograms, times, got to be careful with our signs, negative 1.5 meters per second squared. This is all standard stuff, right? And so when we solve for the normal force, what we get is 750 newtons minus, I don't know what 75 times 1.5 is. It's going to be about 103. Well, don't stare. Calculate. Yeah, so we get 638. 113. There we go. 638 newtons. And our computation tells us, yes, indeed, the person is going to be lighter. They're going to, quote, lose weight while the elevator is accelerating downwards. If we cut the cable, what will the acceleration of the elevator be? What will it be? What number?
No, it would be greater.
If we cut the cable on the elevator, what will its acceleration be? Negative 9.8 meters per second squared. What would the scale read in that case? Nope.
Almost nothing.
It would read nothing.
Well, almost.
Because the MA here would be exactly equal to negative mg, add them, and we get 0. In other words, the person would feel weightless.
Right before they die.
Right before they die. That's right. Okay. Unless we cut the cable 2 meters from the bottom, but you know. Now, let's come back and let's analyze this in a non-inertial frame. We're going to put ourselves in the position of the person inside the elevator now and feel what they feel. In our non-inertial reference frame, we have still mg pulling straight down, and still Fn pushing up, but now we are going to introduce the fictitious force, and that fictitious force is going to be equal but opposite to mass times the acceleration of the elevator. The elevator is accelerating downwards, so here comes our MA, our fictitious force, pointing upwards.
So it always goes opposite of the normal force.
It always goes opposite of the acceleration of the reference frame. Right. And so what value does it have? Well, it has a value of 113 newtons. And so now when I do sum of forces, let me get a little bit of this out of the way here. Not quite like that. There we go. Like this, and like, oh.
Uh-oh. That's not good. That'll be good.
There. This is now out of the way here. Now we do sum of forces on this, and we get, here's 113 newtons, pulling up, plus Fn, minus 750 equals 0. Why is it 0? Because inside the elevator, you aren't moving. There you are. Next floor. There you are, right? There is no motion for you inside the elevator, so your sum of forces has to add up to 0. Well, lo and behold, when we solve for the normal force, we get 638 newtons. There's no surprise there. We didn't expect that the scale would read two different values at the same time, but it is the fictitious force that makes that happen, so that the scale reads the same value whether I'm looking at the scale in the inside reference frame or from the outside. Does that make sense to everybody? Yes.
Do you always have to calculate the internal before you calculate, not inertial before you calculate non-inertial?
Great question. No. The purpose of doing the fictitious force in the non-inertial reference frames is that you can choose whichever one is most convenient for you. You can either look at it from the outside and do sum of forces equals MA, or you can look at it from the inside and do sum of forces equals MA. Whichever one makes more conceptual sense. So let's do a slightly more complicated example where you can see how it might be beneficial to use a non-inertial reference frame. I want to consider I'm going to do it like this. I want to consider the fuzzy dice that I mentioned here. And the fuzzy dice are going to have mass m, and they are going to be hanging from the mirror inside your car, which of course looks like a sign for a bus or something. Okay? And they're just hanging there. Now, the car is going to accelerate. And it's going to accelerate at a rate of 3 meters per second squared. And all of us have enough experience with this to know that when that happens, the fuzzy dice are going to do like that, right? And so we want to know what is the angle between the fuzzy dice and the vertical. Bless you. What will the angle be between the dice and the vertical? In other words, while this thing is accelerating, my dice are going to swing out like this, and we want to know the value of this angle right here, theta. And from a non-inertial reference frame point of view, this becomes very, very easy. So here is our non-inertial analysis. We're going to draw, of course, a free body diagram. And our free body diagram is going to have a tension that's pulling off at this angle, like this. And it's going to have mg pulling down on the dice like that. And now we are going to introduce our fictitious force ma, which points in the opposite from the direction from the acceleration of the car. And that's all you have to do a non-inertial analysis, is to add your fictitious force, which points in the opposite direction from the acceleration. Now that we've done that, we can do sum of forces equals 0, because the fuzzy dice are not moving in their own reference frame, right? Now, we're going to have to do sum of forces in the x and y directions here. I'm feeling lazy today. I don't particularly want to do, well, I could, but I'm just going to do tx and ty instead of messing with sine and cosine just yet, if that's okay with you. And so I can say that the sum of forces in the x direction is tx minus ma, and that has to add up to 0. And the sum of forces in the y direction is going to be equal to ty minus mg, and that must also be 0. Well, that gives us a really easy solution. It means that tx is going to be equal to ma, or 3 times m, and ty is going to be equal to mg, or 10 times m. Everybody with me so far? And finally, tx and ty are pointed in the direction of the rope here, so that if I take the angle with the vertical, then I can do my usual SOHCAHTOA to say that the tangent of that angle is equal to tx divided by ty, which is equal to 3m over 10m. My masses cancel out, and I get 3/10. So that theta is the inverse tangent of 3 over 10, whatever that may happen to be. It's going to be something, I think it's going to be around 15 degrees, but I'm not sure. Looking for inverse here. A second, that'll work. Yeah, 16.7 degrees. So you can see that working in non-inertial reference frames is very simple. All you have to do is to keep in the back of your head, I'm going to have to add one more force into my free body diagram to compensate for the fact that my reference frame is moving. It's really a bookkeeping trick is all we're doing. Yes?
How would you do it in a, just a regular inertial reference frame?
I could do something similar in an inertial reference frame, but there I would set the sum of forces here equal to ma.
Wouldn't that be easier?
6 of one, half dozen of the other. It all depends on how your brain is thinking about it.
So it would be more beneficial to use just the regular inertial one if you think of things more from the outside than if you were in the reactor, if you think about it like that.
I think of this as an additional tool, as a way to move back and forth from one perspective to the other. And whichever perspective is the easiest problem-solving perspective, I'm going to use that one for this problem.
What if it specifically says in the problem, like from the view of the woman,
Then you do that.
she is, so then it would be non-inertial if it were from the view of the woman.
Well, I don't know. Is the woman in an accelerating reference frame?
We'll say so.
Yeah. Exactly. Okay. Any questions, comments, or jokes?